All right. So this is the last session. Charlie, now at Microsoft, after spending his life at IBM, I guess. Yes. Well, tell us about how they're starting to contribute to the JVM, which is also in its way an amazing thing. So take it away. Say a boot a lot.
I'll try. All right, so Marcus introduced me quickly. Charlie Gracie. I usually have my contact information on this slide. I guess it's on the last slide in this talk. So if anyone wants to reach out after the talk, let me know. So today I'm going to talk about the current state of EA in some of the JVM compilers, EA's escape analysis, and different optimizations they use. When I first proposed the talk, it was going to be more of a dive into those technologies because I was going to talk about what we might be able to do in C2. And then we magically got a prototype working, so it'll be more on the prototype with a bit of basic information on those GCs and escape analysis and things, so I can cover more about the prototype we ended up doing. All right, so quick overview, talk quickly about escape analysis, the main optimizations people apply based on the information from escape analysis, quickly cover what different JVMs are doing with those what optimizations they're doing, give some examples of the results of those in practice, some very small trivial examples, and show you where and when that eliminations and stuff can be removed, and then jump into the prototype we did with a colleague of mine. All right. So what's escape analysis? There's two links here, two things from Wikipedia. I won't say any of those verbatim because they're not particularly great in my opinion, but that's how they're described by Wikipedia. So basically, escape analysis is a pass that compilers use to track the lifetime of objects and allocations to check to see whether or not they actually escape the current method or the thread, depending on what you want to do with it afterwards. So it's basically just tracking that to see if it could escape by being passed as a parameter to another method, or it could escape as being a return. And there's all kinds of different, it could be stored into another object, which is known to be escaping, like a global variable or somewhere else. So those are different ways it could escape. And EA is going to go through and try and figure out that so that you can do other optimizations based on it. EA is not an optimization itself. It's just used by other optimizations, which is quite commonly misconstrued in blog posts and different articles online. Some of the other things is you'll see new JIT technologies talking about having partial escape analysis. So Graal is always mentioning that they have partial escape analysis, and OpenJ9 also does something similar. So what that is basically it's a variant of escape analysis where you're not proving that it doesn't escape on any path. You're just figuring out the paths where it does escape and doesn't escape. And if you know it's not escaping on a path, you could still then go and apply whatever optimizations you are along that path, as long as you can handle undoing that on the failing path or merging the results together. So with the results from escape analysis, there's generally three optimizations that compiler technologies will use with the results. So monitor elision is basically removing the locks. So in a given method, if it happened to be a synchronized method or you're synchronizing on an object, if that's known not to escape the current method, then that means it's also not going to be visible to any other thread. So why would you actually enter the lock to do something to then release the lock? Because it doesn't really it's not required because it's not escaping, so no one else could see it. Another general optimization is called stack allocation. So instead of allocating your object on the heap if it's not escaping, reserve a bit of space on your stack on the way in, and then you can just use that memory, and that really helps to reduce heap pressure and can give you some performance wins based on cache locality and those types of things. A noticeable improvement, again, on top of stack allocation is scalar replacement. So this is sometimes referred to as, what's the word? Allocating your object sort of in chunks, or it's like breaking it up, because it doesn't need to be all there. If you may only even be just using one of the fields in that object in this method, so why allocate all the space on the stack? If you can, you just create a local referencing that field and kind of promote it through and use that instead. Oh, yeah. And I think J9 called it something similar to that, but yeah. So scalar replacement can then give you a lot more possible benefits because it can do more it can help do more optimizations. In particular case is if you had a boxed integer that was a known integer always passed in, you might actually then be able to apply future optimizations knowing that it's just an integer that you could go through and do other constant folding and things. Not everyone takes advantage of that depending on the opt, but it is a possibility in the future with that. So what's kind of the current state? So this is, I'm going to quickly talk about the 3 JITs I was able to run and check things out with, and just kind of talk about very quickly what optimizations they do based on EA. So Hotspot C2 EA and its optimizations, there's a very good paper. I'm not going to dig into how EA works there. It's very well documented here, and the implementation is quite straightforward based on the doc. But Hotspot actually applies 2 optimizations. They'll apply lock elision or monitor elision, and they scalar replace. Graal, again, there's another paper you can go read. Any of those deep dives would have all been a talk on their own, so kind of just leaving that for people if they want to know more about it. Again, it's very similar of lock, monitor elision, and scalar replacement. And the difference one here, and this is kind of why I brought up this little section in the talk, is J9 actually does stack allocation as well, along with the other 2 optimizations. There's no interesting paper on how J9 does their partial escape analysis, but that's a link that you could follow that actually goes to the code. Not recommend it reading for an afternoon, but if you really wanted to know how it was working, go dig into that very complicated C++ code. So kind of the kind of key point to my talk here today is this is sort of in practice how and things are working, in particular in C2, because that's what I'm focused on, and that's where I'm kind of hoping to make some improvements. So if we all look at this very simple code, we end up creating some integers, and that'll end up being 3 allocations. And with that, these allocations, if we all look, the method's actually returning an int, which is a primitive. So in fact, none of these actually are doing anything other than boxing, and don't escape. This is to prove a point. I hope no one writes this code. But in a workload like Scala, this ends up being kind of what some of the code looks like to do an operation like this. So that's why it's my example. So if we look at the results, I wrote all this code. If I go back, is here, just little tiny micro benchmarks I wrote using JMH. All 3 collectors here, if you run that, do 0 allocation. I'm asserting 0 allocation from the GC count, and I've verified the logs myself. But I would have put the allocation rate, but OpenJ9 and JMH don't quite play that well together, so it was missing for the J9 one, so I thought this was the easiest. No GCs are happening at all during the runtime once things are compiled. So everything's eliminated, which is really great. And looking at this code and digging into the JIT versions of the code, they've all scalar replaced all of the allocations. But that was the most trivial case. Well, I guess it could have just been allocating 1 and returning the value, but that's pretty much the most trivial case you can get, and it was working. But what's the limitations to scalar replacement? Scalar replacement has a bunch of restrictions of when it can't be used depending on the allocation and what's happening with it. One of the biggest ones when we were analyzing a bunch of different workloads, and it basically happens in every workload, is you can't do scalar replacement on an object once there's been a merge point after some control flow. So in this example, if you look, we come in and we're going to either, if the argument value is greater than 127, we're going to allocate the object ourselves. Otherwise, we rely on a cache. And then all we're doing is returning the value from it. So at this phi in the C2 IR terms, you're not going to be able to scalar replace this. So because of this merge. And you're like, well, why do you care about this particular case, Charlie? That is actually a very common pattern. And in fact, if you look here on the left, you can see that that's my initial code I was using. And on the right is probably how you'd more likely write that code. You would let auto boxing happen. And when you auto box things, it's going to call integer value of. An integer value of has a cache of all of a static cache from -128 up to 127. The maximum is configurable. But what that means is every time you let auto boxing happen, C2 will never scalar replace your object.
This wouldn't be a problem unless someone put this in the JLS.
Yeah. So this is here, and the world's simplest cases here now can't actually have scalar replacement done on them. So again, how common is this? I ran the workloads. That's basically the same code. We now have 2,000 GCs when you're running with C2. You'll have 0 with J9 and 0 with Graal. The first note beside the Graal number, let's start, I guess, with OpenJ9. OpenJ9 stack allocating the objects. Stack allocation has a lot less restrictions, which I'll cover later. And so they can still stack allocate. You'll notice that they took a bit of a perf hit from their previous one, which is in like 60 million. But they're still able to do it. Graal has no allocations because when I dug into it, when they go to inline or do something with integer dot value of, they recognize that at parse time and keep a special IR node that knows that it's that, doesn't include the conditionals to begin with. If it's scalar replaceable, they scalar replace it. Otherwise, when they come to gen the code, then they generate the conditional code they would reference from the static array. So yeah, and it's quite noticeable in there. So I'm not sure that was quite fair for my analysis, so let me quickly change my code. In this one, I'm going to simulate integer value of by actually just writing my own wrapper class that has an int in it. And when we go look at that, magically, now with Graal, we have thousands of allocations again. The total number of allocations and ops here, this is running on my desktop. It's just to point out that there are a lot now. And again, J9 doesn't, because they're stack allocating the objects when they fail to scalar replace them. So I guess the one thing is, I think it would be a reasonably good work item to possibly do in Hotspot to actually do something similar to what Graal is doing for that integer value of operation. I think it would be quite simple and something that we're going to talk about on the mailing list once I get back. And hopefully that might be something that we do as a precursor to some of our work.
Quick question. I found out when we did Nazareth that we really lacking good escape analysis. We were really lacking good escape analysis when we did Nazareth and work with invoke dynamics, with auto-boxed everything. And we tried to like look at things like partial escape analysis and Hotspot, and we found, and maybe I'm biased again, but the sea of nodes is an incredibly hostile representation to do partial optimizations on anything. So we didn't have the cycles to do this.
That when we started looking at it, this mostly came from some of my previous experience and seeing some failures on other areas when I was working, and then looking at workloads. And Kirk, who's here, was mentioning that a lot of Scala Spark workloads see huge wins with Graal because of their partial escape analysis. So I said, well, we should. And going to look at, I'm like, well, let's look there. That's workloads we want to help optimize. So when we started looking, the sheer work to go to a flow-sensitive partial escape analysis in C2 was something that I think would provide some wins, but that was going to be a much larger item, especially for us to tackle, not knowing C2 yet. That was going to be a lot of work. And I wasn't 100% sure that it was required to get the wins. More serious inlining or smarter inlining heuristics may also help and work with the current flow insensitive analysis that's happening. And so when we actually started gathering a lot of data here, C2, when you're running in fast debug, you can output information about everything that happens in EA, all the objects, allocations, whether or not they're escaping, and if they can be scalar replaced. So many were properly being recognized. Like anything that I could find in a hot code path, C2 was recognizing as not escaping. It just couldn't scalarize it. So we thought, let's go down this path and look at stack allocation. So to back up a little bit, could you actually scalar replace these things if you just improve scalar replacement in some way? So if we look at the previous example again, and the code here in red, before there was a return after the else. If you had some optimizations in the compiler that you could hoist these up, or like the read up, or do those types of things, it would be possible. But again, that's a lot of work, and depending on the way you're moving things, it might actually cause some side effects. And I think someone's asking a question in the back. Yeah, so the question was about a recent optimization in C2 for splitting the phi's. We looked at stuff with tip as well, as we've been tracking what's going on, and it does catch in some places some of this, but it's still a lot of other places it's not catching it right now. But I think maybe this trivial one in tip might actually have that happen. But once you get into some more complicated loops, I found it wasn't happening, but I'd have to dig in further again. So with this, we decided that we could do a bunch of work here too, and other people in Hotspot were already looking at some of these things. So we decided to move over, and because we wanted to do stack allocation, because we were able to see that on a lot of these ones, J9 was still able to remove the allocations. Now they do have a partial escape analysis similar to Graal, so we were trying to decide whether or not it was because of that they were still able to do it, but it felt like just the ability to stack allocate was enough. So in our previous example again, if we came through, and instead of when you were coming through, if you actually allocated your stack allocated the object, that's a full object. It has all of the same header fields, has the marked bits and a class. It's just where the memory is that it's been allocated in. So in that case, this merge down here was completely fine. We can still stack allocate in that area, and then you're good to go. So again here, stack allocation, if we were looking at some of these examples, would allow you to basically catch a lot of the cases. So in this case, you have two boxed integers. Coming into the method, those are okay. If you just get all of that stuff, it kind of gets you a win, but it's the big win comes from when you have a bunch of them happening in loops. So that allocation every time in the loop, is doing a lot, especially depending on the following code afterwards. Like if you're actually going and fetching fields and things, and this can be pretty big wins. In particular case, when you're doing useless things like just returning the int here. So it's unboxed, everything dies. Let's just actually go and stack allocate them. So what if C2 had stack allocation? So my simple value of method again on my object. This is the results from before, no change to the chart. And if we had stack allocation, we were able to successfully get it. So again, it has no allocations or GC activity. And the relative performance win is okay. This one isn't really doing much. It's mostly math work happening. So how much can we improve the math? We've just stripped out the initialization, some of the initialization, and some of the cache misses from going to the heap. But you also get the win from the GCs. Yep. Better inlining, better math. Dan has a question in the comment, or I cast it in the back. There's the answer from Dan. The question was, why was C2 better than both Graal and Hotspot? Graal and J9 before this. J9 guy said that he was they had a bug that they're fixing in scorching. And sadly, I don't know anyone from Graal here to answer that question for them, but haven't dug into that too much. I was kind of hoping this little chart, that column, people might not pay too much attention to. But I thought I wanted to show the win for the hotspot one. What's the stack allocation? So how do we implement this in C2? So the first step was to actually go into the escape analysis phase, and whenever an allocation was being rejected from scalar replacement, we then continued on to see if we could stack allocate it. We would never want stack allocation to happen if scalar replacement could happen, because it's just a win. So we only look at allocations that aren't escaping and that aren't eligible for scalar replacement. That's still not every object that's not escaping, but it can be quite a few more. So we had to modify there. And then when it came to the point when they're basically going to generate the code, or not generate code, change the IR for inlining the allocation steps in, we just recognize the allocation that we marked as stack allocatable and basically cut the slow path and a bunch of the TLab workout and just use the location on the stack. And it was actually quite easy in that area to put it in. But how did we reserve this memory on the stack? We tried a few different things in the beginning, and there's a lot of very complicated code that relies on knowing everything in there. So the easiest path for us to do the prototype, and again, this is prototype code. We were going to work with a bunch of the C2 guys to try and make it real. They have the idea of a box lock. So this is where there's slots on the stack that they use for doing monitor operations in C2 already. So you could tell it where you want it to be, and then you can just work with this node in their IR everywhere, and when it gets to code gen, it knows how to go fill in the proper offsets into the stack and stuff for you for your instructions. So to go forward, we would probably have to refactor this because it comes with some weight that we wouldn't want if this was the final solution, to have sort of like a super class of these nodes that was just stack location node or something. But we use this to be able to go through and do it. The other big one is now we had to change the GC to handle the fact that there are objects, that aren't actually in the heap. The C2 collector is very full of assertion. The Hotspot GCs are very full of assertions and checks to make sure, especially when running in debug, that if you think something is an OOP, it's on the heap. So we had to make sure that it didn't get down into anywhere lower into the GC. So we put a simple layer on top to be able to, and then some of the OOP iterators to be able to specifically handle a stack object so that it was out of there. This is one of the areas that where we want to talk to the C2, the Hotspot developers about to see what would probably be the better way of doing this, and to be able to handle more collectors. Right now, I believe we only work with Parallel and G1. I haven't tried Shenandoah or ZGC, but I have a very sneaky suspicion we would run into lots of subtle bugs where things weren't working right. Part of the expansion to escape analysis is we actually had to figure out if there were any overlapping live ranges of objects in loops. And I'll talk about that more on a future slide, I believe. And we removed write barriers for all of these objects because they're fully tracked from the stack, similar to the scalar replace ones. They didn't need any write barriers right now with the current solution. That might change in the future. And we completely just reuse the heapification. That's probably my term. I'm not sure you see that word in the Hotspot code base. That's where there's deop points or places where you would need to go back to the interpreter places. You actually do need a real object, but we just completely relied on the solution that was there for scalar replacement. It was already tracking, well, we just had to create the right object. It was all just tracked everything for us. So again, quite simple and straightforward to get that going. So to quickly cover the root scanning, on your stack normally, you would just have pointers or regular primitive data. Now at this point you can see this is just a pointer to another object, and then here we're going to have our object just allocated directly inline in the stack. You can see if you've ever dug around in a core file, the flags field for most of objects on allocate in some collectors is that value. This is its class pointer, and again, just a pointer to another object. All of these are following through at the bottom of the stack after the spill location. Overlapping live ranges. So this one was one of the gotchas that both Nicola and I were completely aware of, but then forgot while we were writing the code. And then very quickly, some benchmarks and regular code found it. When you have the first allocation outside of the loop, and then you can see down where if we stack allocate of both value and result, at any point when we would come into the value doesn't equal result section and set value equal to result, since that stack allocated object is going to use the same memory all of the time, no matter what your equals check is there, if it's checking the pointers at some level, checking the values, they will always be the same from now on once you've gone in there once. So you would never come in again. So we had to, this was one of the enhancements we did, or one of the changes we made in escape analysis was to detect these live ranges. So current limitations. We don't stack allocate objects in methods with monitors or synchronized methods. That's because we're taking advantage of the box locks, and there's some changes to the offsets they do based on eliminating allocations already. This is completely doable, just wasn't doable before I got here. And we don't allow stack allocated objects to be referenced by other objects. Clearly a heap object can't reference it, that's an escape. But even right now, we don't allow stack allocated objects to point at other stack allocated objects. This is one of the areas where if we got this working, we would see even more wins. This is pretty common, and there's a lot, especially in Scala workloads again, there's a lot of wrapper classes holding on to other objects. So this would very quickly give us more wins in those areas. But it requires either more analysis during EA or us to modify the write barrier and make it quite a bit more costly. So we weren't willing to go that route before we talked to everybody. So more limitations right now. We don't support compressed oops. The main reason is the stack pointer is not in the heap range, so you can't compress and decompress it if you're going to store it or have the other things stored into it. We have some ideas on how to solve this. But again, something we need to talk about to make sure we go down the right path, because that's going to be real work. We don't want to spend too much time just to have people say, hey, you guys who don't know C2 yet, this was easier, you should have done it that way. Arrays are similar to ones with monitors, just didn't get to it. It should be quite trivial. And then once we messaged the mailing list, we were quickly pointed out that we were forgetting about Project Loom coming in and very fast stack swapping. So we might have some work to do there, or at least turn off some stack allocation on certain save points. Oh, sorry, if they run into certain save points. So we have this working prototype. How does it perform? So on a bunch of the Scala workloads that we've measured it on so far, we're seeing improvements. At this point, because we haven't done some of the more complicated work that might require write barriers or things, we haven't seen anywhere where that it's a cost yet. Maybe minor increases in compilation time because we do a bit of extra work, but in actual throughput and things, we haven't noticed any losses. That could happen if we start doing some of the more complicated parts. But at this point, the most standout one is Neo4j at 45% improvement. And then a bunch of the other ones are on like 5, 10, 15%. Looking at GC logs and different things from these runs, it's not all just in GC time going away. Some percentage of it is, but a lot of it is actually, you'll see actually a lot less stalls on loads, memory loads and things, because your stack is almost always in your cache. A newly allocated object regularly isn't in your cache or anyone's cache. So that's where we believe a lot of the wins are coming at this point. So it's there, we talked about it, we sent a message to the mailing list. If anyone saw that, you'll notice that there was no patch associated with it. That's great, we're talking about it, when are you gonna see it? We had done our prototype on JDK 11. Just it was happened to be while we were working on for other things. We're in the process of moving it to tip. As soon as we get it moved up to tip and verify that things are still working, it'll show up. I hope it's not very long from now, but we're hoping that it'll be there soon. So what's our next steps? First is get the patch on to the mailing list. 2 is kind of stabilize it. There is one known issue right now with our patch, and it's around GCs and the way that we're tracking oops in the oop map. We're just digging into that. We're pretty confident it's not a showstopper in any way, but we want to just have that so that we can pass all testing when we put a patch out there. We had that list of limitations before. We want to work through those and get rid of them. I suspect a lot of that would happen if we get this in afterwards. I know a lot of folks are probably like me, and the smallest possible working thing go in and then further improve it. So I'm kind of hoping maybe that's how things would go, but we'll see as we start talking about it more. Of course, extend GC support, work with the ZGC and Shenandoah people to see what we're going to break and what we need to do to make things work there. And then go back and revisit, look for more workloads, and then measure all of the total costs and things so that we have a very clear picture of where things are truly at. This is our contact information. If you want to reach out, hopefully we start being a lot more active on the Hotspot compiler dev mailing list, maybe some of the GC dev mailing list. So check us out, check out the threads there. Contact either myself or Nicola, the other person working on the prototype with me. Anytime, we're happy to answer questions or talk about it. And that's it. Any questions?
There are some Hotspot Jet guys in here in the back that might have something to say. They'll be happy to look at the code. So tell us about this initiative. initiative that Microsoft is doing now with like JDK and why and how? How many are you hiring?
Total numbers, I don't follow what we have on things. There's a bunch of engineers like Kirk, here's myself, Nicola, and other people. I believe we have open hiring tickets, but they might be too junior for you. But the initiative is to, what my role is on the team is to work with the community to help improve Java for workloads everywhere. I would be not truthful if I said it. Azure wasn't something that if we helped Azure, that would be a good thing. So that's of course there, but I think this will be my personal opinions that Microsoft has been taking a lot more active role in open source. So and communities that are being used by their customers, I think they want to be able to take part and help out and make sure those communities are thriving because it will just help their customers and user base. Oh, there's one question here.
Question, or just to continue with your comments, I think one of the focuses is that as workloads become more cloud-based, I think Microsoft has taken a real stance on saying they just want the best Java experience or the best runtime experience for the customers in the cloud. So our role within Microsoft is really to help make that happen. And so Charlie's focused on specific JVM work, but there's other things that are happening in terms of tooling spaces and things like that that we're also working on to help make that happen. But one of the things we want to make sure that happens is that everything that does happen actually makes it back out into the community also. So there should be more community involvement coming forth.
All right, if there's no more questions, I'll give you guys back a few minutes.